Hello, everyone. My name is Reha. I am a second year PhD student at the University of Florence in Italy. And I just want to, before I start off, I would just like to express my gratitude for being invited to speak at this series. I've been attending it from November last year, and it's quite cool. And it's a good honor to be on the other side exactly a year afterwards to present some of my first year PhD research on spatiotemporal fault evolution patterns in magma-rich rifts using quantitative geomorphology. And my study focuses on Central Afar in East Africa. So starting off, a quick background on the Afar Depression. So the Afar Depression is very famous for being a classic triple junction where three rift boundaries meet. So in the Afar Depression, these are the Red Sea Rift, the Gulf of Aden Rift, and the main Ethiopian Rift, which is a branch of the East African Rift system. Quickly zooming in to Central Afar, which is my study area, as it's highlighted on the map on the right. Central Afar has been studied to be a linkage zone between the Red Sea Rift and the Gulf of Aden Rift, and the linkage zone between their magmatic segments, which is the Dabahu Mandahararo at the DMH and the Asal segments, which are highlighted in orange on the map on the right. Past studies have also shown that linkage within this central Afar zone has been active for at least 3 to 5 million years, but the mechanism of linkage, that is the kinematics, the dynamics, age progression, etc., remain debated. Also, a quick background on Central Afar in particular. This is a beautiful geological map of my study area, which shows the lithology. The lithology within the study area, that is the black rectangle, is homogeneous throughout, which is basalt and is characterized as the Afar stratoid series, which were erupted as sheet flow basalts from the late Pliocene to Pleistocene. A quick note on the climate. From the late Pleistocene to the present, the climate within the zone has also been classified as relatively arid and dry, and the area receives less than 300 millimeters of rainfall per year. A quick note on the structural features within the area, as shown by the beautiful 3D views on the right. Within the structures are characterized by normal fault-bound graben systems. The major graben systems are around 30 to 60 kilometers in length, and they trend primarily west to northwest, east, southeast, which are the red lines in the diagram. These major grabens are cross-cut by subordinate graben systems and minor intersecting normal faults, which trend north-south, which are marked by maroon dotted lines on the diagram. The area is also characterized by simple isolated drainage networks, as you can see a few of them that are highlighted in this figure, like R24, R25, R26, that clearly originate on the footwall of these grabens and cross the normal fault and drain into the hanging wall that is on the graben floor. So it's clear to see that the streams cross these normal faults. So we know that these are the structures in the area, but what do we know about the rift linkage mechanisms from past work that has been conducted in this area? Older models, such as these ones on the left, from Manighetti et al. 2001, for example, are based on paleomagnetic data, and they show that the linkage occurs via bookshelf faulting, which is known to be where the segments overlap, and there are left lateral strike slip faults within this rift linkage zone. But more recent studies, which are based on INSAR and geodesy, have shown that there's not exactly an overlap between the two segments, but between the two segments is what they call a rift step-over zone, which is a broad zone of extension. And numerical modeling efforts have also been done to understand how the strain transfers and migrates within this extensional zone. So therefore, the main aim of my study is to understand the mechanisms of rift linkage in Central Afar in terms of the structural features and the spatiotemporal evolution of the graben systems that I talked about earlier. And for this, I will be using a method called quantitative geomorphology. Quantitative geomorphology is a tool that has long been used to quantify landscape signals of tectonic activity to better understand evolution of faults, how they link and grow, and their timescales. As highlighted in this methodology, if a river is cross-cut by a normal fault and if there is constant uplift on the footwall, the uplift triggers the river's erosional response. So the river basically incises to keep pace with the active uplift. And because of this incision, a nick point is created, which is a break in the channel slope, which are highlighted by the blue stars. So the evolving channel, while the channel profile evolves, which is clearly convex up, the nick point migrates upstream as highlighted by these graphs. I've also, and the block diagram, and I've just found a good example of these beautifully incised canyons in central Afar. And the rate at which the nick point migrates and the age of the nick point initiation can be used to tell us fault initiation timescales using the stream power law. Amongst a whole suite of other geomorphic parameters that go into the stream power law, in my study, I will be using the bedrock erodibility, which is the inherent property of the rock to be eroded, the amount of vertical incision, the area of the catchment and the channel slope, and the age of the bedrock, and these characters together link landscape evolution to tectonic activity. So my main aim would be to use a combination of geomorphic and structural analyses to constrain spatiotemporal graben evolution in central Afar. So first, I will need some catchments to analyze. For that, I processed a 30-meter DEM from the SRTM data, which allowed me to delineate my catchments, create a stream network, generate the long profiles, and identify the nick points that breaks in the slope. I did this using ArcGIS Pro, using the spatial analyst and hydrology toolboxes, and conducted further geomorphic analyses using the topo toolbox functions on MATLAB. And I verified all of my results by manual geomorphic mapping on Google Earth's high-resolution aerial imagery. And from that, from this map on the right, I identified these 26 catchments across the 7 grabens from north to south in the region. And these are what I will be using for the fault initiation studies. Specifically for the geomorphic analyses, I used 2 Dobie graben catchments. So Dobie graben is the center of is within the center of my study area as reference sites for the geomorphic calculations. So here, firstly, I computed the erosion rate, which is the minimum rate of erosion that's required to create the nick point. And followed by that, I estimated the bedrock erodibility using this equation here and the velocity at which the nick point is retreating upstream, that is from the outlet to the location where it is today. Once that was done, I applied an iterative approach to calculate how long it must have taken for the nick point to reach its present day position. And once this was done for the Dobie graben, and once the bedrock erodibility was estimated, I could use this for all of the other catchments in the study area and then obtain a similar age and velocity values for everything. Once this was done, I also extracted the swath profiles, which is the fault relief profiles for the 7 major graben bounding faults, and they are highlighted by their respective colors on these maps. And this was done to further establish a relationship between the fault relief and the elevation of these nick points and to see what that can tell us. Once all of this was done, so these are my results. These are the river long profiles, which are the plots of elevation against the distance downstream. As highlighted in the methods explanation I did earlier, all of these river long profiles are convex up with clear breaks in the slope, which are marked by the stars, and they are the nick points. And the nick points also, as you can see, are located at a distance upstream from the fault, as highlighted by the squares. And this shows that the rivers are exhibiting a transient landscape response to the tectonic activity in central Afar, and they are actively recording and reflecting this tectonic activity. Coming to the swath profiles, they broadly follow this bell-shaped trend of the relief gradually decreasing towards the fault tips. Plotting the heights of the nick points above the fault, which are these stars, it shows that within error, most of these nick points plot on the footwall crest, which tells us that the nick points were created as a result of the fault initiation. To further and explicitly test this relationship, we plot the height of the nick point against the fault relief. And as highlighted in this graph, they are related to each other in a clear near linear relationship, which confirms that the nick points were formed due to the initiation of the fault and not due to any other later or prior tectonic activity. And when the fault grew, that triggered the erosional response and the nick points were created. Therefore, the age of nick point formation that we find in our method section can be equated to the fault initiation ages of the main graben bounding fault. And from this graph, we see not so clear a trend, but a good trend that the Dobie graben, which is the center of the linkage zone, is one of the youngest, with ages of initiation of about 0.5 to 1 million year. To further understand the fault activity dynamics in central Afar, we computed the minimum throw rate, that is the footwall component or the uplift component, for each of the main fault systems. And this one has a better trend to show that the throw rate is increasing towards the center of the depression. And the Dobie Graben has the highest throw rates, reaching up to 0.8 millimeters per year. Therefore, to say where most of the deformation today is concentrated, we see that the Dobie is the most active and can be called, as you say, the locus of primary present-day deformation. From this graph, and in combination with the age graph that we had before, we see that all the grabens are active in the sense that they accommodate the extension to various degrees, and the strain is dynamic, and it migrates from graben system to graben system as time progresses, probably over 0.5 to 1 million year timescales, and while Dobie is currently where most of the deformation is localized presently. Using all of this data, generated a spatial model of graben evolution within the rift linkage zone. So to start off, the linkage, the oldest grabens are around 2.8, 2.7 million years. So this shows that some of these graben systems were initiated around that time, followed by two other graben systems towards the north of the study area, and the further propagation of the magmatic segments. And then closer, and then after that, where most Dobie and the other younger graben systems were initiated. This graph also highlights the activity where Dobie, the thickest line on Dobie, indicates that it is got the highest throw rates and therefore is currently the most active graben system. And to support this, just to check this against recent seismic activity, for example, our results are supported by the seismic activity catalog that I've got from USGS that shows that most of the current strain is very clearly localized on the Dobie Graben, again, showing that most of the extension is here and Dobie is therefore the most active. And where does this fit in with the other rift linkage models that we've had in the past? Our model shows that the primary linkage mechanism is created by the formation of n-echelon normal fault-bound graben systems within this rift step-over zone. And by the age and throw rate relationships, we see that individual graben systems are active for about 0.5 to 1 million years, and then the strain activity transfers and migrates to newer graben systems towards the center of the linkage zone. We show that it's not really a broad zone of diffuse extension or anything, but it's more localized extension that progressively migrates. And our results are also, they complement recent numerical models that have shown that there is strain transfer and n-echelon faulting within the area. Basically, our results highlight that there's dynamic and migrating strain, which localizes and migrates, and the Dobie Graben is currently the most active. And these are some of my key conclusions from the study, is that the Nick point retreat metrics have helped us constrain the onset of faulting in the area. Therefore, the linkage has been active for at least about 3 million years. The extension is accommodated over 0.5 to 1 million year timescales, and the extension progressively localizes towards the center of the linkage zone. The Dobie Graben, as I've said a few times already, is the center, has the highest throw rates and is the current locus of deformation and activity. And the rift linkage mechanism, as shown by our model, is a distinct structural style that is not really related to some of the past models, but encompasses a few features from each to show that there is localized deformation that is accommodated by n-echelon normal fault-bound grabens in central Afar. So this summarizes most of my results in research from the first year of my PhD. And that's it from me. I'd just like to thank my supervisors and my co-authors team for their support along the way. And thank you very much. I'm open to any questions.
Thanks, Reha. That was great. So I open the floor to questions. If you just put your hand up, I should notice, or put it in the chat. Here's a hand up by Robert. Do you want to feel free to?
Thank you. Very, very well delivered and quickly delivered talk. Hard to keep up with you, but I think I did. A question. Do I understand that you have considered the climate a constant?
Yes.
If, for instance, the rate of, let's say, the rainfall had been higher between 1 and 2 million years ago, how might that affect your conclusions?
That's an excellent question. So as I mentioned, the stream power law takes in a variety of parameters, and then the change in rainfall would have affected the amount of incision and all of that, and then the amount of sediment discharge that would occur in the area. And so that basically I would use another version of the stream power law where the constants, the M and N, were different to account for these parameters. And based on like rainfall modeling, I would look at it in the way, I guess, depending on what the actual circumstances were, but then modify the version of the law and the constants accordingly to consider that.
So how would it change your estimate of time evolution?
I guess that would, because obviously increase in rainfall means the rainfall and the climatic conditions are contributing to the erosional rate. So I guess that would broadly decrease the time that I find, because that would also be contributing, and it's not just the tectonic activity. So there would be an interplay between both of the factors. So I guess my age estimations would be the maximum age estimates, considering that I've only assumed that these are being affected by tectonic activity. So they could be lower if the rainfall was to play a part in this.
Mm-hmm. Could you look at the sediments in at the mouth of the rivers to get an estimate of the erosion rates in the past?
Yes, I could. That would be one of the other approaches I will employ. That was going to be one of the next steps I'm going to do to further refine my analyses based on some of the fieldwork I'm going to conduct. Just later this month, I am traveling to Afar to be able to do this. So that will make part of some of this analysis in the future to refine and fine tune these measurements.
Thank you.
Okay, thanks.
Thank you very much.
Sasha?
Yes, great talk. Thanks, Reha. One quick question on the impact of the lava flow layering on the erosion rates. Do you think that has any bearing on how you interpret your stream power laws and then the Nick Point retreat?
So the layers. So some of the past work that I just read, I have taken as the whole chunk to be the Afar stratoid basalt that there was a river, and then the lava was in place, and then the uplift happened. So I've taken it to be one homogeneous lithology throughout the study area and throughout the fault section. But then this is another thing that the fieldwork could help fine tune, that if there were different, and then the different lithologies would mean different erodibility values. And then that would mean that I take in a few other estimates, and then that would give me a range of erodibility. And then that would further expand my ranges of my calculations, so on and so forth. For this, it was one of the assumptions was made was that because it's the same like Afar stratoid basalt series throughout the study area. So it was good to be that the erodibility is relatively constant throughout because the rock type is the same. But of course, there are different parameters that can affect this. But assuming that it was homogeneous, again, it would all be maximum estimates, and then these could change as we go on.